Okay, so now we're going to give you some intuition about one of the big theorems that we're ending this class with, and that's called Green's theorem. We're just going to start it with the flux divergence form. And I'm actually just going to give you the conditions. So you need your vector field to have continuous partial derivatives everywhere inside the region R. So this is R. Here is my curve C. And you can imagine now we have some vector field. Let's call it F. And I'm just going to make up what it's doing. Maybe it's water, maybe it's gas. It could be anything we like. It could be an electric field. It doesn't always have to be going the same way. I can kind of just make it do crazy stuff. But this is my vector field F. And I'm interested in calculating what the flux, the outward flux around the closed curve C is of my vector field. So I'm going to do F dotted with N and then ds. Okay, so this is back to a line integral. Let's do ds in a different color so you can see. Okay, this is back to a line integral, and so what's important here is that I'm not talking about the flux outward through the page. I am talking about a two-dimensional vector field, and I want to know how much of it is crossing the boundary if I'm looking at this as being my n. So I want to know how much of this fluid is flowing outward from this region, not outward out of the page in 3D, because my vector field is not three-dimensional, it's just flat two-dimensional. You could picture water on the ground, and this is like some little boundary that I've traced out, and I want to know the net amount of water that's passing outward through this boundary. Okay, so we know one way to do this, which is what we did last lesson, which is actually just to parameterize the boundary and do this line integral. But now we're going to learn a theorem that's going to connect what's happening on the boundary to what's happening on the interior of the region and use that information instead. So I'm going to leave you hanging for a minute and not tell you what we're going to do quite yet until we prove it down below. All right, so what we're going to do is rewrite our vector field F as PIQJ, and then we're going to imagine chopping up the entire region into a bunch of little subrectangles, and we're going to approximate the flux across just one of those little subrectangles inside the region. And I'll show you why. So chop up R into rectangles delta A. And we'd like to approximate what the flux is across. And we're going to get to that in a minute. I'll show you how. But then, once we do that, I want you to imagine that we've approximated the flux across, say, just this little subrectangle right here. Once we've found what that flux is, we're going to add the flux across that rectangle with the flux across the rectangle right below it. And notice, because I'm really thinking of flux outward, let's do my normal vector for this top curve will always be pointing to the right, which means the normal vector for my bottom curve is going to be pointing to the right of where I'm going. So on this little line where they share in common, my outward flux should cancel, because we're going to be thinking of how much of the vector field is passing outward through the top one, and then add that to how much is passing outward through the bottom one, but those should cancel each other. And so we'll end up with the net outward flux just through this shared region here. And that's what's going to happen when we sum up the flux across all the rectangles on the inside. And then notice, so eventually here, if I summed it up across all the rectangles in the inside, I'll get the flux just across this weird shape here. And then if I take the limit, as I chop this up into smaller and smaller pieces, I will get the total outward flux. And so notice what we're going to end up doing is forming a limit over Riemann sum. In this case, I'll be taking the limit as delta A goes to 0. And so we're going to use what's happening on the inside to help us calculate the flux across the boundary. So let's go up and calculate the flux across one of these tiny little subrectangles, and then we'll come back to that big picture. the idea is I've blown this, just imagine this is like blown up a little bit. We've taken one tiny little rectangle here and we've blown it up, and that's what I'm now looking at right here. That's this entire little rectangle. And so we're going to approximate the flux across this rectangle. We're going to approximate it across each side. And just remember, to define flux over here, what we're really doing is adding up the F, like the force vector dotted with the normal vector at a given point, and then times a little delta S, and we're adding that up and taking the limit. So flux is going to be approximately the sum of these F dot N delta S's. Oh, let's make delta, I want to make my colors consistent, of course. I want this delta S to be blue so you can watch what happens as we move along. Okay, and once we've proven this once, we'll be able to just use Green's theorem. I just want you to understand where it's coming from. So we're going to approximate the flux across the top by evaluating the vector field at any point along the top. So I'm just going to pick the top left corner, and I can pick any point here along the top, because the idea is that we're doing this for such a small little rectangle that the vector fields, we're going to assume it's approximately constant along that top bound, and so we can pick any of the points and we'll get the same vector field. And then we need to dot it with the normal vector. And so just sketching it, you can see the normal vector along this top boundary is just going to be j hat. And the normal vector along the right back boundary here will be I hat. And along the bottom will be negative j. And along this side will be negative I. Okay, so here we're just going to dot this with j hat. And as a reminder, j hat is just 0, 1, 0. And then we're going to multiply by delta S. And along this top boundary, delta S is just going to be the same as delta X. And so notice what happens when we actually take the dot product of my vector field F here with j hat. I'm just going to get the j component of the vector field, which will just be Q, and then evaluate it at that left corner, X, Y plus delta Y, and then times delta X. So go ahead and put this on pause and see if you can find the flux across the other three sides, and then we'll come back together. Okay, and so this is what you should get for the flux across the other sides. And now we're going to put that all together. We'd like to add the total flux on each side of this rectangle and see what we get for the net outward flux through the whole thing. So let's just start by adding the flux across the top and the bottom, which is just adding this and this. And notice this looks, the numerator of it, I mean, this itself looks like the numerator of an expression that we saw back in chapter 11. If you're noticing, this kind of reminds us of when we were finding a partial derivative. In fact, if I divide both the numerator and the denominator, let's do it with a different color, by delta y, then this whole piece right here is going to be approximately the partial of q with respect to y, and then times delta x, delta y. And then same thing we can do with the flux across the right and the left. You can notice that if I multiply and divide by delta x, that this whole thing is going to be approximately equal to the partial of p with respect to x, and then times delta x, delta y. Which means the total flux across one rectangle will be, if we add these together, approximately equal to the partial, I'll just start with the p1 first, partial of p with respect to x plus partial of q with respect to y, and then the delta x times delta y, that's just delta A. But notice, we've seen this. In fact, we saw it on the previous page when we were just doing a basic example right here. Given a general vector field here, G, the divergence is defined as the partial of P with respect to X plus the partial of Q with respect to Y. And so here, since my vector field was F, we're just going to write this as the divergence of F and then times delta A. And this is what we got along one of the rectangles, and we can add this, we can do this along all the other rectangles. And again, the idea is when I'm doing a line integral along one curve here, let's put the line integral along this curve of f dot n ds is the opposite if I go along the exact same curve and go the other way. And so they'll cancel out when I add them together. I'll get 0 along their shared boundaries. And that's what we're seeing is happening right here. So if I add the net flux from this rectangle plus this rectangle, I'm ending up getting the net flux outward through this new rectangle. And I can do that everywhere on my region, and you'll see that if I'm adding it up along all these ones inside, it'll eventually be telling me the net flux through this region. And then I can take the limit as delta A goes to 0, and that will get me the net flux through the boundary because it'll become nice and smooth. And so notice what's going to happen if I take the limit. I've added this up. This is my quantity. I'm adding it up over all the rectangles. So I'm going to get a double integral over the region R of my integrand will be the divergence, and then the delta A in the limit of the Riemann sum will turn into dA. And so let's go back up and put this into the top, put this into our theorem up here. And what we've just shown is that instead of looking at what's happening on the boundary and integrating a line integral around the boundary to figure out the flux, we can actually add up or integrate the divergence everywhere on the interior, and we will still get the same result. This is giving us two ways to find the net outward flux. So this is dA. Okay, so notice this is net outward flux because we defined it looking for the outward flux. And what's cool about this is then you can then interpret this. If this whole quantity here gives me the flux, then I can really think of this as a flux density because integrating it over the interior leads to the total flux through the boundary. So that's why in that video we were saying, oh, this divergence measures the extent to which something is acting like a source or a sink. It's because if we add up the divergence everywhere on the interior, then we're going to get information about how much of this vector field is flowing outward across the boundary.